All right, and I'll just get started by saying welcome everyone. So this is the follow-up to the Pulsar timing workshop that we had over the last couple of days. And we'll be using some of the skills that you learned in those days to time some real Pulsar data from Meerkat. And what's special about this is that no one in the MeerTime collaboration has looked at these pulsars in detail yet. So when you run some analyses to find new timing models and to find the noise characteristics of the pulsars, you'll be the first people to do that with this data set. And the hope is that if you're dedicated and we get some good results out, we will be able to write a small paper about these timing analyses of these pulsars. So I'm going to turn my video off just while I'm showing screens to keep some more people joining, just to keep my internet stable. So let me share some slides and I'll describe what we'll be doing in a bit more detail. So this meeting will be a little bit more casual than the workshop. So I don't mind if people want to yell out if they have questions along the way. It's only a small group, so that should be fine. But if there's too many questions, well, I can defer them and we can pick up later. Okay, so first of all, in the Slack channel, you should have had a link to download the data collection that we'll be working with. So Marissa has hosted the data on the FTP server, and you can grab that link and enter that into your VirtualBox and download the data to the virtual machine as we were doing in the workshop. Okay, so let's get started. If anyone needs workshop revision, then, or if you find anything particularly confusing, then these will be good resources for you to revisit. So these are the recordings for the lectures. In particular, I think lecture 6 is probably the most relevant to what we're doing now. And in fact, I've taken some figures from Ryan's talk to use in this one. Lecture 7 as well, but that was only recently uploaded, so I will update these slides with the link shortly. So by the way, the link to these slides is also in that Slack channel, so you can follow along with those, because later on we'll have some commands to type in and we can just copy and paste. All right, so what is the recipe for timing a pulsar? This is very close to a slide that Ryan had in his lecture 6 on his recipe for timing a pulsar. So first and foremost, you need to record what you do. And we have Slack channels dedicated to each of the individual pulsars that you'll be looking at. And so in those Slack channels, you can type comments like, I'm doing this and I'm doing that. And I found these results, and you can post parameter numbers, you can post screenshots, and it's just great to keep a record of what you're doing so that myself and others can give feedback, and also we can trace what was done to arrive at a certain result. So this link is to a document with some notes that I put together on analyzing one of these pulsars. And we'll be going through this pulsar in this talk, just as a demonstration analysis. And you should be recording a similar type of document when you're analyzing the other pulsars. So yeah, that's just something to keep in mind for the whole process. It's important to record what you do. Now, the first step is always just to understand your pulsar. So look at the existing scientific literature, look into the Pulsar catalog, and I'll show you how to do that, and understand what telescopes and data has been analyzed in the past about this pulsar, because that should give you some context about what results you can expect from MeerKAT, given that MeerKAT is a more sensitive telescope to most others that might have been used in previous work. But at the same time, our data sets are most likely shorter because we've only been monitoring pulsars for 2 years. Right, so once you've done a literature review and you understand the pulsar, the next steps, which are highlighted in yellow here, are to reduce the data and form your times of arrival from the observations. So these are in yellow because these have already been done for you, but we will revisit how that was done, because it's possible that after you do your initial timing analysis, there are aspects of this data reduction that we could go back and change. So this has been done just as a starting point, but we could go back and revisit this. But the basic steps are to calibrate the raw observations that came from the telescope, remove any RFI, which is radio frequency interference, and to reduce the dimensionality of the data. So reduce the number of frequency channels, reduce the number of subintegrations, and form a pulse profile, which is total intensity. That is, we remove the polarization information. Then from that data, you form a standard template. This will be your model of the pulse profile. And using that pulse profile, you then time the pulsar using the template matching technique. And it's kind of like in my data analysis introduction notebook, how we were sliding the template profile over the data to find the reduced chi-squared value, or the smallest chi-squared value. That's exactly what happens in this process. And we did that also in Aditya's exercise. Okay, so once again, that's all been done. Now, this step is where you'll be picking up. This is where we've already got our pulse times of arrival. And we would like to fit the timing model to this. And this part is relevant to, or was discussed in Ryan's lecture and the exercise that followed that. So we use Tempo 2 to add and subtract new timing model parameters to the model. So for example, this could be the pulsar parallax, which gives us the distance, or it could be parameters that describe the Shapiro delay. So we look at what is already in the timing model, and then we see if there are any new parameters that are significant additions to the timing model, and we use statistics to do that. We'll also use TempoNest to solve the noise environment in the pulsar. And I mean, we search for parameters that describe any pulsar's spin noise, any dispersion measure variations, as well as white noise parameters. And I'll go into these noise parameters shortly, but if you need more of an in-depth look at that, then Ryan's talk is where to go for that. Then we basically iterate these two steps, because the timing model parameters and the noise parameters can be related. They're both new additions to the timing model, and they can be correlated with each other. So if there are any changes to the noise model, you can look again for timing model parameters in Tempo 2. And if you add any new parameters in Tempo 2, you should search again for the noise parameters. So you iterate between these two steps until you think that you've found the optimal solution, the best timing model, that is. So if you think you're done, if you've iterated these tests and you think you're finished, what you'll see is that the Bayesian evidence returned by TempoNest, this is one of the statistics we'll look at, the Bayesian evidence will be maximized. Out of all the analyses that you've done, one certain combination of timing model parameters and noise parameters will maximize the evidence. And the reduced chi-squared value should also be very close to 1. So at that point, you look at what you found. So what new timing model parameters did you add? What noise properties did you discover? And at this point, we can go ahead and simulate further observations because we think we understand our pulsar. So we can generate fake data, which is just simulated data to be taken in the future. And we can see what effect that has on the timing model parameters. And that will tell us whether it's worth taking Meerkat and pointing it at this pulsar for a certain amount of time to discover some interesting physics. Okay, so that was a lot, but I'll go through these in more detail in the next slides. So again, this is what we're looking for. So in the timing model, the timing model includes the deterministic terms about the pulsar, and there's also a noise model that goes with that. So the noise characteristics include jitter, which was introduced in Ryan's talk. This is pulse-shaped variations from observation to observation. Red noise, which is also called timing noise, and spin noise. This is intrinsic instability in the pulsar's rotation, and dispersion measure variations. Right, so these are the primary noise sources that we will be searching for. In the deterministic timing model, we will be looking for evidence of frequency evolution of the pulse profile, improved orbital parameters, maybe a parallax, which again gives us the pulsar's distance, maybe a Shapiro delay. So the Shapiro delay was described in a lot of detail in Federico's lecture, which was lecture 7. But just to refresh, this is what the Shapiro delay looks like. So this is the timing residuals for a pulsar that was observed with Parkes. And this shape is a time delay caused by the light from the pulsar passing through curved space-time of its companion. And because this is a relativistic effect, this allows us to weigh the companion and also solve for the mass of the pulsar. So this is something that was done in Federico's exercise. So if you would like to learn more about that, you can revisit that. Okay, so once we've looked at the noise parameters and the timing model parameters, we also just would like to assess the quality of this pulsar for timing. So what are the typical uncertainties on the times of arrival? And what is the weighted root mean square of the residuals? This is the standard deviation of the residuals. So this will allow us to simulate future observations and then predict improvements in the timing model if we were to carry out those observations. All right, so just to revise on these noise processes, again, have a look at Ryan's talk if you need a lot more revision. This figure was taken from Ryan's talk, actually. But the first process we'll look at is just white noise. And white noise is called white noise because it's uncorrelated between observations. And if you were to take a power spectrum as a function of frequency or as a function of color, then the spectrum would be flat, meaning you have equal contributions from all frequencies or all colors. And so this is why we call it white noise. So this can arise because of pulse-shaped variations, which also contributes to jitter. And the way we model this in our noise model is to make adjustments to the measurement uncertainty so that the reduced chi-squared value is 1. And these equations are from my lecture 4 slide describing what the chi-squared value is. It's the sum of the squared deviations from the model, or the weighted sum. And the reduced chi-squared value is this divided by the number of degrees of freedom. And basically what this means is that if your uncertainties are too small, such as in this bottom panel here, then the reduced chi-squared value is much bigger than 1. And what that essentially means is that the uncertainties don't accurately describe the amount of scatter that's in our data. So we will always be fitting for white noise parameters in our noise analysis. The question is whether we also fit for additional noise terms. So the next noise term we'll look at is timing or spin noise. We also sometimes simply call it red noise. And these are correlated, where the residuals are positively correlated from one to the next. And this has the effect of creating these long timescale variations in the pulse arrival times. And Ryan mentioned in his talk that this looks like a cubic, but actually this is a power spectrum of variations. So in this inset plot here, we look at the power spectral density as a function of the fluctuation frequency. So this is basically we're looking at the Fourier domain now. And so this long timescale variations translates to excess power at low frequencies. Right? So this is what that red power spectrum looks like. And this can be caused by intrinsic spin irregularities in the pulsar. It can also be caused by errors in our solar system ephemeris, so the model that predicts the light travel time between the telescope and the solar system barycenter. And it can even be caused by gravitational waves. So you're likely to find some red noise in some of these pulsars that we'll be looking at. And this, again, is just modeled as a power spectrum. So there's two parameters. There's the amplitude of this spectrum and the slope of this spectrum. I'll just go back and mention that actually so I mentioned that the parameters we fit are adjustments to the uncertainties. There's two parameters for that. There's a scale factor, which we can just simply inflate the uncertainties by some factor. But there's also a term that we can add in quadrature to our measurement uncertainties. So there's two white noise parameters typically. We do also have an option for a third parameter, which describes white noise that is correlated between observations taken simultaneously. And what I mean by that is multiple sub-bands in frequency, but taken at the same time. So that's an optional third white noise parameter that we will look at. So 2 or 3 white noise parameters, 2 red noise parameters here. And the next process we'll look at is dispersion measure variations. These are a lot like red noise in characteristic, in that they have a red power spectrum, meaning that they're stronger at lower frequencies. But the important way to differentiate them is that the amplitude of this process scales as 1 on frequency squared. So it's much larger at lower frequencies. So in this plot, I'm showing the timing residuals for a particular pulsar observed with Parkes as a function of a long data set of many years. And the red timing residuals are from observations in a 40 centimeter wavelength, so a low frequency. The green is a 20 centimeter wavelength, so a bit higher frequency. And the 10 is the blue is a 10 centimeter wavelength, so an even higher frequency still. So you can see that there's this similar structure, this wavy pattern in the timing residuals, but the amplitude of this pattern is much, much higher at the lower frequencies. And so this is a frequency-dependent red noise process, and it's caused by real changes in the interstellar medium. So when you look at this and you make a measurement of it, you're measuring physics. What you're measuring is the changing column density of electrons along the line of sight. And this dispersion measure may also have deterministic components, including linear or annual variations. And this, again, can be related to physics. So for example, a linear trend could be caused by the pulsar's radial motion. And so over time, more or fewer electrons could be between us and the pulsar if it's moving through a dense environment. Okay, so that just about summarizes the noise parameters we'll be looking at. And so now we'll look at the timing model. So on the left here are some examples of errors in the timing residuals that you might see if certain parameters in the timing model are incorrect. So in the top left, this is just white residuals. This is saying that the timing model is perfect. There's nothing else to be fitted here. In the top right, we have an error in, I think, the position. This is an annual sinusoid. In the bottom left, we have a parabolic shape. And this says that the pulsar's spin period derivative is at the wrong value. And this on the bottom right is, again, an annual sinusoid, but it's growing as a function of time. And this is an error in the proper motion. Now, in your pulsars, when you look at them in tempo 2, you're not going to see anything this obvious. We're trying to add, trying to see if there's evidence for new parameters in pulsars that already have some pretty good timing models, but that doesn't, so basically you're not going to see this by eye. What we'll be doing is using statistics to see if there is evidence for additional parameters. So things we could be looking for, the position is generally fitted in all of these pulsars except for one, and that's the one I'll be going through in the demonstration. So the dispersion measure is also the dispersion measure derivatives. So the first derivative of dispersion measure, time derivative that is dm1, and that is a linear trend in dm. So the parallax, which gives us the distance through just parallax equals 1 on distance. And the way this works out is in units is that milliarcseconds is 1 on kiloparsec. And this comes from well, the units seem weird, but this comes from a small angle approximation in the definition of a parsec. We could fit for proper motion terms. So this is the proper motion in right ascension and proper motion in declination. Frequency dependency of the pulse profile, and these are captured in FD1, FD2, FD3. These are the coefficients of a polynomial fitted as a function of log frequency. So FD1 means that the timing residuals against log frequency have just a linear shape. FD2 would mean that there's a quadratic. Okay, and finally the Shapiro delay. So the Shapiro delay can be parameterized with the companion mass and the sine of the inclination angle, but they can also be parameterized with these other parameters, which I can give you a link to the paper that describes these, but these reduce correlations between the two parameters, and these are the ones that we'll be using. Okay, so now we'll go into an example analysis. So we'll go through this pulsar now, and this is just demonstrating the kind of thing you'll be doing with these other pulsars that are available. Right, so first of all, if we go and look at the recipe that was at the start of this observation, we need to do a literature review of the pulsar. So how do we do that? The first thing to do, well, the first thing I do is just search for the pulsar's name and see what comes up. So when you do that, the first thing that comes up for this pulsar, which is really cool, is the MeerTime database, actually. So you can click on this and look at some of the data that has been collected with Meerkat. But if we look a little bit further down, there is actually a very recent paper by Duncan Lorimer on timing observations of 3 galactic millisecond pulsars. And this pulsar is one of them. So I was really glad I found this paper actually, because this is very similar to the kind of paper we would be hoping to write on these pulsars once the analysis is finished. Okay, so you can search the pulsar's name and see what comes up. You can try to find the discovery paper, so the paper that first announced this pulsar. And you can also look in the pulsar catalog. So this is the web address, but you can also find it by typing in PSR cat and find the pulsar catalog that way. So let's say you found a paper that you're interested in, such as this timing observations paper. You might have a link that takes you to this NASA's ADS website. And if so, you'll see a page that looks like this. So that link on the previous slide takes you to this. If you're able to access the paper from the publisher, you should see a PDF icon next to here. But if not, then easy access is from archive.org. And so that would be this PDF symbol here. And this would bring up the paper. Okay, so once you've got the paper open, what are the key pieces of information that you're looking for? So by the way, this is a link to this paper if you want to have a look. Well, the key pieces of information are basically you're trying to find out what previous data sets have been used to analyze the pulsar that you're looking at. So you might want to answer these questions. First of all, can you find the discovery paper, either referenced in some other paper or just find it on your own? So it's actually in the abstract here. So this is the reference for the discovery. And basically, I'd like to answer how much data did they analyze and with which telescope for this pulsar? And the answer from this paper can be found in this table of parameters, which has the pulsar's name. So they used, well, first of all, the Parkes radio telescope, that's in the abstract here. And they also used 24 observations over 547 days. Now, they didn't write that specifically. The way I found that was, first of all, the data span. So this is in units of MJD. So if you just subtract the n from the start, that gives you 547 days. And the 24 observations, I only had a quick skim. I couldn't see this written specifically, but they say that the number of degrees of freedom in their fit is 12. And so thinking back to the reduced chi-squared equation, the number of degrees of freedom is the number of data points minus the number of parameters. And this table shows you how many fitted parameters there were, because a fitted parameter is one that has an uncertainty associated with it. And the uncertainties are here in the brackets. So if you count these and use the number of degrees of freedom, then you get that they had 24 observations. So what timing model parameters did they measure? Again, in this case, there's just a table of them, so you could just record this table somewhere. And how precise was the data they were using? So they had a data set of 28.8 microseconds in root mean square or standard deviation. And again, that's given in this table here. So these are relevant pieces of information because when we look at our data set, we actually have fewer observations, which might mean that we're not able to fit as many parameters as they fit. And we also have a shorter data span for this particular pulsar. However, Meerkat is a lot bigger and better than Parkes. And so we have a better timing precision. And so there's a trade-off there. And it's just good to keep these numbers in mind so that you can compare your data set to that previously in the literature. Okay, and as you're going through the paper and you're searching for the pulsar's name for any mention of it, take note of anything interesting that stands out to you, that maybe you want to read about in future. So for example, there's a couple of interesting references here. First of all, they have an estimate of the pulsar's minimum companion mass. And they say that using the orbital period, this paper predicts that the mass should be this. And so to me, I'd say, wow, that seems interesting. There's a way that we can predict the companion mass using an orbital period. And so you might want to go to the references to follow up this paper if that interests you. And they say, if true, then the inclination angle would be this. And then later on, they say that the orbital eccentricity can be predicted from its orbital period as well. And there's a reference for that. So you might want to look at these papers if that interests you, and see how, what equations they use in order to predict, or equations or models that they use to predict these things from just the orbital period. Okay, and finally, using the Pulsar catalog. So this was the website for the Pulsar catalog. I might actually just quit out of the presentation and show you how this works. So I'll use this Pulsar 0900-3144. This is another one of the pulsars we're looking at, because it's funny, I couldn't use 0921 for this because it actually wasn't in the catalog, which is a bit weird. Since it was discovered in 2012. Anyway, so if we go to the Pulsar catalog over here, so the way you use this is you scroll down to where it asks for pulsar names, and you can type in the pulsar that you're interested in. And then you can ask for any particular parameters that you want. Let's look at, first of all, the J name, the position, the proper motion. Let's look at the dispersion measure and maybe the orbital period. Okay. So once you're—
Daniel, are you able to just zoom in a bit, maybe?
I don't think so.
Okay, no problem.
I'm scared if I zoom in, I might not be able to zoom out. Okay. So once you've selected the parameters you want, you hit this table button. And it will show you the parameters that you've asked for. So the pulsar's name, the position and right ascension, declination. But more importantly, they have these references next to them. So this first reference next to the pulsar name is going to be the discovery paper. And this reference next to the parameters are going to be probably the most up-to-date analysis of this pulsar to date. So you can click on this. This is a link, and it will take you to the paper that these parameters came from. And so that's another easy way to find the references for this paper. So in this case, it actually came from an analysis of the European pulsar timing array. Okay, so you could just copy this and paste it and find the paper on archive that way. Okay, so back to this presentation. Okay, well, actually, I'm going to jump into the data now. Maybe this is a good point to stop and ask if there's any questions so far. Nothing in the chat, Marissa, or Slack? I can't really see.
Nope, I'm keeping an eye. I don't think so.
Okay, so we'll move on to the data. First of all, I'll describe what has already been done to the data. And then we'll talk about the state that the data's in when we hand it over. All right, so this follows a lot of what we went through in Matthew's lecture and Aditya's exercise demonstration that followed it. this is reducing the size of the data and also cleaning it. So first of all, we've removed any radio frequency interference from this data. And that can be seen in this bottom plot. So this is showing the intensity as a function of pulse phase. So you can see that the pulse is here in the middle, and it's got this funny sort of 2 or 3 components, but this is just one pulse from the pulsar, one rotation of the pulsar. But as a function of frequency, there are all these horizontal lines of basically 0 power. And those have been removed because there was man-made interference, so radio frequency interference. And that's been removed from this data. So there's many frequency channels here. You can see that there's a very fine channelization in frequency. There's also many sub-integrations. And so this is now looking at the data as a function of time. So down the bottom here is the start of the observation. And then as a function of time, we have every 8 seconds or so, we have a sub-integration and a plot of the pulsar's intensity. So what we've done is we've scrunched in polarization, and by that I mean turned the pulse into just total intensity. We don't have any polarization information. And we've reduced this very fine channelization in frequency down to just 16 channels. And that should be enough to capture any profile evolution across the band, so any change in the pulse shape as a function of frequency. But it's also greatly reducing the size of the data. And we've also fully scrunched in time. So we don't have any of these sub-integrations. We just have one sub-integration. And if you're interested in revisiting, if we were able to send you the raw data somehow, this is the command that was used to do this data reduction, where star underscore zap.ar means all of the cleaned observations that are in this particular directory. And by the way, these are the commands used to create the plots that I'm showing. Okay, so the next step was to form a template. So we sum all of the data together. So all of those reduced data, we time scrunch the combined data. And we have 2 ways to create a template. We can either leave all the frequency channels as they are, so there's 16 frequency channels, or we can sum in frequency or scrunch in frequency to form just a one-dimensional template. And once we've, one-dimensional pulse profile. And once we've done that, we then smooth the profile using wavelet smoothing, which Aditya went through in his exercise. So the commands to do this are PSR add, and minus T means T scrunch as we go, all of those previous observations. And then we do this PSR smooth command to create a smooth template. And what we're left with is this model of the pulse profile. Okay, so once you've reduced the data and you've created a template profile, then it's time to actually time that data set using this profile. And so this again was shown in Aditya's exercise after Ryan's lecture. But we run this command pat and ask it to print out all this information and use this FDM algorithm to do the timing. But basically in this step, what we're doing is we're sliding the template over the data in order to find the phase shift that gives the minimum chi-squared value. And once we've done that for each observation, we write the results out to a TIM file. I see that Sam A has a raised hand.
Sorry, just a question. Can you go back to previous slide?
This one?
For the back, the one before that. So my question is, because I remember during the exercise, there was a step where we did RFI excision interactively. But my question is, so to get the .zap file, you guys were running the paths to get it automated.
Good question. Yeah, so we used PASI in the exercise to do it interactively, as you said. But that is really just to give you a feel for it. Because we have so many observations, we use an automatic algorithm. PAS is one such algorithm, but we actually use something else that was written in Python. And the idea of that algorithm is to basically subtract off a template of the profile and to tell us where the on pulse region is, so where the pulsar is actually on. And then we do statistics on the off pulse region. And using those statistics and the expectation that this noise should be Gaussian, we can remove anything that's not Gaussian. So that's how we do that. Yeah.
Okay, so it is something standard then, if I understand correctly. You don't need to sort of customize it somehow, or depending on the data.
Yeah, it's just an algorithm that we run on all of our data now.
Oh, okay, thanks.
Okay, so once you've done this template matching procedure on all of your observations using your template, you send it all to a TIM file. And again, we did this in Aditya's exercise. And what you're left with is something that looks like this plot, where the columns are the file name, then the observing frequency, then the time of arrival, uncertainty, the telescope name, as well as a bunch of flags that describe various properties of the observation. Okay, so this is where your project starts. So maybe I'll just stop once more and see if there's any questions. We already had one, but is there any questions about the data reduction? Okay, no questions. So I'm just looking at the time. We should have a break at some point, but maybe I'll just go through the first stages of this and we can have a break and then come back and continue on. So I'll continue for now. This is the part where this is the part where you'll start for the other pulsars. So all the pulsars that you'll be given data on. And we'll be looking at this pulsar 0921 first of all, simply because the data set is not very good. It doesn't have many observations. And so the ones you'll be given are much more exciting. Okay, so we run this command to view the data in tempo 2. So what this is doing is saying we'll use this timing model. So this is the initial guess of the timing model that you'll be given. And this TIM file, which has important flags in it. This is what the underscore flag means. And we use also this select file, which says that we're not going to analyze any TOAs from the pulsar if the signal to noise was less than some cutoff value. Okay, so once you run this command, you'll see a text output in the terminal that looks like this. If you scroll up a little bit, and you'll see a plot that comes up, which looks like this. And these are your timing residuals. So at this point, the first thing to note is which parameters are being fitted and what is the RMS residual in this case, the weighted RMS residual. So these arrows show what you should be noting just at this initial point when you first plot the data. So when you first plot it, you'll note that the weighted RMS is 17 microseconds. And in this table, anything that has an uncertainty is being fitted, right? So in this case, it's only the dispersion measure variations. And that's the only one being fitted. which is why it's the only one that we have an uncertainty for. Okay, so at this point, you inspect your timing residuals, and you look for any obvious signatures. So if we think back to many slides ago, we saw that there could be very obvious signatures in the residuals, but in this case, you're not going to have anything because I at least think that I've got this these initial parameter files in a state where you should plot something and get a reasonable result that should be ready for the start of a noise analysis. But in general, these are the types of parameters you will be looking at adding on, but we'll be mainly doing that after a noise analysis. Okay, but when you're inspecting the times of arrival and the timing residuals, this again is a zoom in on the plot that would come up when you run that command. It's important to visualize the residual not just as a function of MJD, which is what on the previous slide, which is what this plot shows. It just shows your timing residuals as a function of the MJD of the observation. Sorry, that's been cut off. But it's important to play with these buttons on the left, which change the X coordinates and the Y coordinates of the data that's being plotted. So change this to, first of all, post-fit residuals. So this shows the residuals after fitting for this highlighted parameter, which is DM. It's the only parameter that's fitted in this case. And then look at the residuals as a function of year. And that will just allow you to very easily visualize the time span, because I know lots of people, myself included, can't visualize MJDs very well. So also plot as a function of frequency, which is what I'm showing here. So post-fit residual on Y and frequency on X, which gives us this plot. So this is the low frequency data here and the high frequency data over here. So if you have any strange structures in here, then you might need to think about fitting for these parameters. So the DM1 and DM2 describe the first and second time derivative of the dispersion measure. And FD1 and FD2, as I said before, are coefficients of a polynomial as a function of log frequency. So they would be modeling some polynomial structure in this type of plot. Okay, and then you plot as a function of day of year. And if you have any errors in the pulsar position or the proper motion, or even the parallax, you're likely to see some structure as a function of day of year. And finally, orbital phase. So if you're, if there's any errors in the orbital parameters, which include these ones, so PB is the orbital period, A1 is the projected semi-major axis, T-ask is the longitude of ascending node. This is the reference epoch for the orbital parameters. And EPS1 and EPS2 are the eccentricity times the sine of the longitude of periastron, and the eccentricity times the cosine of the longitude of periastron. These are called Laplace-Lagrange parameters. Okay, and one final thing to do is to, if you're in a plot as a function of time, so for example, date, or as a function of year, when you're in this window, you can press Shift-R, and then in the text box, it will ask you to select a flag and an epoch over which to average your data. And this is important because our times of arrival, if I go back to the previous slide, our times of arrival have multiple observations occurring at the same time. And this is because we have one TOA from every frequency channel in one given observation. So because we had 16 frequency channels when we reduced our data, we have 16 times of arrival at the same time. So this Shift-R command will allow us to average those together into a much smaller uncertainty point, and it will allow us to see signatures in the times of arrival that have lower amplitude. So they might be hidden in this structure. We just can't see them on this scale. So again, to do that, you hit Shift R and then choose a TOA flag to average over. And I suggest just using -F and an epoch over which to average over. And I suggest using 0.1, this is in units of days. Okay, so that should average together all of the subbands in one observation. Okay, and just to note on this command down the bottom here, we have shortcuts to, well, first of all, -US puts the Y scale in units of microseconds, and then this yplot2, yplot7 says which parameter to plot on the Y and the X axis. So this would be a shortcut to get to this plot here, but you can also do it interactively, as I said. Okay, all right, now we're up to analyzing in TempoNest. I think what we'll do is, in the next 5 minutes, I'll just show you how to open up the data in the virtual machine and run these initial Tempo2 commands. And then we'll have a break and talk about TempoNest. Okay, so let me stop sharing my screen. And if you have your VirtualBox open, now would be the time to go to that and you can follow along. Let me share. Okay, so you should now be seeing my VirtualBox, is that right?
Yeah, we see it clearly.
Excellent. Okay, so if your VirtualBox is open, and if you're struggling or you'll need help with that, then you can just observe and maybe watch this recording back at a later time with a working VirtualBox. Okay, so let me just remove, well, okay, no, I'm going to remove that. So you would first of all download the data using this command, which Marissa has put in the project Slack channel. So wget and then this link to the data. Okay, but I've already done that. So if I type ls, I'm in my share directory and you can see the files that I have. So I have this project.tar.gz. What I want to do is type tar -xvf. And again, this command is also in the project, the research project directory. Okay, so if I run that command, I get all of these outputs. And you can see now that I have this project directory that has been created. So, okay, maybe on Zoom, give a thumbs up if you're following along live, or if you're just watching me on Zoom do this, don't put a thumbs up. So thumbs up if you're doing this yourself. Excellent. I have 4 thumbs up and a raised hand. Hand's gone down. I'll assume that was meant to be a thumb. Okay, I have a raised hand. Is that a question? Okay, I'll assume that's not a question. So if you have any trouble doing this, so just put some description in the Slack space and we can get to that at another point. Okay, so everyone who said that they were following along, have you downloaded the data and do you have this project directory? Give a thumbs up if yes. Okay, I'm seeing thumbs, so I'll take that as a sign that I can continue. So what we want to do is go into this project directory. So cd project. if we type ls, we can see what's inside that. We have a folder called decimated, and this is just another word for reduced. So this contains the data that's been reduced in size. And we have a script, reduce data.shell, and this is what I use to produce that data. But you don't have the raw data that went into this, but if need be, we can share that with you in the future. Okay, so let's cd into decimated. Okay, and type ls again, and you can see that we have some scripts that were used to create the data. And we also have several directories of the pulsars. So let's now cd into 0921, oops, J0921, minus 5202. Okay, and if we type ls minus L to get a list, you can see that these are the files that are in this folder. There's several .p16 ch t files, and this is p for polarization scrunched, 16 ch for 16 channels, and t for t scrunched. So these were the reduced data files that were output from that script. We also have some other files which were generated in creating generated in the process of creating the standard templates, and this J0921 minus 5202.std, that's the standard that was used to time this pulsar. So we have a tim file, and we also have an underscore flag.tim file. So we'll be using this underscore flag.tim file because this includes important information about the instrumental offsets. Okay, so now I think we're ready to type in that command that that I had. Sorry, let me go find it so I can paste it to you in the chat or something. So yeah, on slide 17, if you're following along in the slides, but I also put it in the Zoom chat here. So this command here, I'll just paste it in. Tempo2 minus grplk, which means bring up the graphics plugin, minus f, the pulsar's par file, and then the pulsar's underscore flag.tim file, and then this select file, which is located at a directory above us. So 2 dots means go one directory higher, and then grab this file. So if we run that, you will see this output. Okay, and so when you do this for the pulsars that you'll be allocated, as I said, the first thing to do is note which parameters are fitted. There's a couple of ways you can do that. First of all, the fitted parameters will be highlighted in red at the top here. So here we're fitting for DM, but also in this text output in the terminal, you can scroll up and you'll see that the dispersion measure is the only parameter that has an uncertainty. Okay, so yep.
I was going to suggest let's just have a quick pause in case somebody fumbled with getting the plot up.
Yep.
We can just give people a couple of seconds.
Yep, sure.
Is everybody comfortable with copying and pasting commands to their virtual boxes?
Yes. Can I have a question?
Sure.
Sure, of course.
Could you please scroll up a bit? The terminal, yeah. You said that the parameter that we're fitting for is have uncertainty, right?
Yep.
But then, like right on top of the table, it says number of fit parameters 10. So we don't take that into account. We only look at the uncertainty.
Ah, you have a very good eye. Yeah, so there's actually some secret behind the scenes constraining parameters.
I see.
And the reason for that is this is a bit technical and we'll get to it later.
No, it's okay. You can come back to it later.
Yeah, well, I'll just quickly mention that if we actually look at the parameter file, this is another way to see which parameters are being fitted. So this is a list of the parameter names and their values. And then this flag 1 means fit for this parameter. But this file also contains information about instrumental jumps, which are down here. And this is why we have those flags in the TIM file, because these jumps are describing those flags. But I've also put this parameter down here, which is an E-core parameter. This is describing correlated noise. So that correlated noise process I described, where this is a noise term that's 100% correlated between observations taken simultaneously, but uncorrelated from observation to observation. And this parameter is actually constraining the fit. It's actually forming, or doing some kind of averaging and then adding in an extra noise term. So it's actually not doing anything in this case, but it will be doing something when you run noise analyses later on. But that's the reason why that's there. So just in short, I'd say that, yeah, ignore that and count the parameters that are being fitted in Tempo 2 and the ones that have uncertainties. Okay, so I'll assume that people have this up now. So really, this is just a demonstration of what you should do once you get here. As I said on slide 18, the things we need to look at, first of all, the post-fit residuals. So click this second Y, post-fit residuals for the Y coordinate. And then have a look at these residuals as a function of, what did I say, year, first of all. So you can see that we have, well, over a year time span here. But there's big gaps in the data that are missing. And so this might affect our ability to measure some of these parameters. But in your other pulsars, you'll see that there's many, many more observations and probably closer to a year and a half. Okay, so the next thing to look at is as a function of frequency. And this is the plot that I had in the lecture slides. The weighted RMS here is different to what I have in the lecture slides because I I've changed the data a little bit before since I made this. But anyway, what we're looking for here is any obvious structure. And here, this looks good to me because you can see that the data are pretty flat and the uncertainties seem to well describe the amount of scatter that we're seeing. The next thing to look at is day of year. So if we had an error in the pulsar's position, that causes an annual sinusoid. And so you would see some structure in here. And the last thing to look at is orbital phase. So if the pulsar has a very strong Shapiro delay, you're going to see a spike at an orbital phase of 0.25, which is when the pulsar is behind its companion. In this case, we don't see anything. Okay, so I'll assume people have clicked on the relevant X coordinates. So now, as I mentioned in that slide, we need to average these subbands together. So once again, every epoch here, we actually have 16 observations taken on top of each other. And that's because if we go to the frequency tab, we've got all these observations as a function of frequency, but many of them are taken at the same time. So in this window, in the timing residual window, hit Shift and then R, and you'll see that in the terminal, it will say average on flag and epoch width. So if you click in here and type -F space 0.1, this will say average on the F flags, or the TOAs that are flagged by this F flag and average every 0.1 days of data into one point. So if you hit enter, nothing will happen, but it will say averaging TOAs on next fit. And then in your window, you can hit the refit button. And then you'll see that all of the data points become averaged together. And what this means is that you'll be able to see any low signal to noise signals in these times of arrival. And in this case, there isn't any, but this might be different in the pulsars that you're analyzing.
Daniel, there's in the chat somebody saying, I missed that. So Nate, do you want to say exactly what you missed? We can just repeat it.
So I assume they missed the averaging. So
probably.
Let me hit this restart button. So when you first open up the tempo 2 command, you'll see your timing residuals as a function of date. So when you're in this window, you want to hit Shift and R. And once you've done that, it will show in the terminal window some text output down the bottom. It will say average on flag and epoch width. And this is described in the last bullet point in slide 18 as well. So once that comes up, you type in -F 0.1, and this will average together all of the TOAs flagged with -F on an averaging window size of 0.1 days. So if you hit enter, it says averaging TOAs on next fit, and I've broken tempo 2 somehow. Sorry. So -F 0.1. Oh no, I've broken tempo 2. Oh, okay, sorry, I just had to hit refit and it fixed itself. Okay, so that might have happened to other people, I guess. Okay, yeah, so Shift R to bring up the averaging, you choose a flag and a window, and then hit refit in this window, which is the button on the near the top left. And once you do that, you'll see averaged TOAs. And this is important to do for your pulsars to search for signals in the data that have a low signal to noise. So it gets washed out by all the many subbands and you can't see it unless you average. Okay, so that's all I wanted to show for now. If we have a small break or if people want to keep playing with that, that's fine. But I think we should have a break and come back and talk about Tempo Nest. So how about we meet, oh, it's my dog's making noise. So it's almost 8:15 UTC. Should we meet at 8:45? Does that sound reasonable?
That sounds great to me.
Yep, so just over half an hour from now. Okay, then I'll see you all then.
Cheers.
Thank you.